right, so hopefully everyone can hear me. Maybe if I can get a thumbs up from someone, if you can hear me.
Yes.
Yes, okay, excellent. So welcome everyone to the inaugural workshop on deep declarative networks. We're, I guess, the guinea pigs of CVPR, or I guess us and the other workshops that are being held today. So hopefully there won't be too many glitches. If there are, we'll try work our way through them. Of course, everyone who's already online has worked out how to join the Zoom sessions. So this will be the main Zoom link. We'll have all of the invited talks and the oral presentations through this Zoom link. And for the poster presentations, if you have registered at CVPR, then you can find links to the poster presentations via the CVPR website. So let me just get my mouse to the right place. Okay. Conventional deep learning architectures involve composition of simple feed-forward processing functions that are explicitly defined. And of course, we're all very familiar with data processing graphs and neural networks, convolutional neural networks, and so on, where we have these processing blocks and the functions of these processing blocks are explicitly defined. But recently, researchers have been exploring deep learning models with implicitly defined components. So to distinguish these from conventional deep learning models, we call them deep declarative networks, where we borrow the naming from the programming languages community, where there are declarative and imperative programming models. Some people refer to these nodes as implicit nodes in a graph, and so we sort of use the terminology implicit node and declarative node interchangeably. So the thing that's sort of different about these declarative nodes is that rather than having an explicit function, we have an implicit function, and in particular, this implicit function is found by solving an optimization problem. And so we replace the explicit functions, in this case function 3 and function 7, with an argmin. And then everything sort of looks normal in the forward pass, where we replace the function with this optimization problem and then compose the network as this composition of functions. So processing nodes in deep declarative networks involve solving this optimization problem in the forward pass, and the question then becomes what happens in the backward pass. So to enable end-to-end learning, we need to be able to backpropagate gradients through the node, and that requires being able to differentiate through these optimization problems. And there have been quite a few papers in the last few years from sort of 2016 onwards that's looked at this problem of computing gradients backwards through these different optimization problems. So this idea of declarative networks or differentiating through optimization problems has appeared in a number of areas in computer vision, including video classification, image attribute ranking, in meta-learning, outside of computer vision in areas like model predictive control. And there've been a fair number of variants of these deep declarative networks. So in particular, for imposing hard constraints on the output of networks, neural ODEs, satisfiability problems, so SATNet, fixed point iterations, and differentiating through combinatorial submodular functions. So the idea of this workshop is to place all of these ideas where we have optimization problems within the neural network. So we're not just optimizing to learn the parameters of the network, but we're actually optimizing in the forward pass and sometimes also in the backward pass. We want to take all of these ideas and put them under a common umbrella and explore how the links between these different ideas, possible shortcomings, and advantages. So the topics of the workshop include declarative end-to-end learnable processing nodes, differentiable constrained and unconstrained optimization problems, in particular differentiable convex optimization problems, imposing hard constraints in deep learning models, backpropagation through physical models, which is particularly important in computer vision, so we can back propagate through geometric models, for example, and then applications of the above in computer vision, such as differentiable rendering, as I said, differentiable 3D models, reinforcement learning, action recognition, meta learning, and so on. We've got a very exciting program with 6 invited speakers who are all experts in the field. So Brandon Amos, who will be speaking first from Facebook, Ricky Chen from the University of Toronto, Chelsea Finn from Stanford, Pascal Foy from EPFL, Subhranshu Maggi from UMass Amherst, and Zico Coulter from CMU. In addition to the invited speakers, we have a number of paper presentations. They'll be given as both orals and poster sessions. So here's the schedule. I should say for most of you, the time looks good. For those of us in Australia, it's 2 a.m. in the morning, and I usually come to conferences complaining bitterly about having to travel far and jet lag. I'm actually missing being able to complain about that, and now I have to complain about being up at 2 in the morning. But anyway, here's the schedule. So we're going to start off with the invited talks. So we've got 3 invited talks, and then that's going to be followed with the paper orals, poster presentations, and then another set of invited talks. For those of your friends who are on different time zones and not here at the moment, we repeat the program 12 hours later, but the talks will all be recorded at that point. So we'll be recording the talks during the first repeat, the sessions now, and then we'll be playing those back later. The only exception is the poster session, which will be live both now and at the 12-hour repeat. I should say as well that the poster presentations will be in individual Zoom meetings. So this meeting room will be for, this Zoom meeting room will be for one of the posters, and then 4 of the other posters will be in different Zoom meeting rooms. You can find links to those on the CVPR website. So I should say as well, actually, in terms of logistics, as I said at the beginning, we're sort of the guinea pigs. We're hoping this will all work without any glitches. If you do find that you somehow get logged out of Zoom because we as the hosts do something stupid like end the session, just click on the link again and rejoin. The way we'll handle questions during the invited talks and the paper orals is through the chat in Zoom. So one of us will chair the sessions, and then the other workshop organisers are going to monitor the chat sessions, and then we can feed those questions to the speaker at the end of their session. If for some reason you've got a burning question and we don't notice in the chat, there's a facility in Zoom where you can raise your hand. That should get us our attention. As a last resort, you can always unmute your microphone and shout out your question. Okay, so I think that's it in terms of the logistics. Here are the websites. Probably the most important one is the first one that's got links to everything, and that's the one that we can update sort of in real time. And but as I said, for the poster sessions, you'll need to go to the CVPR website and have a login there. All right. So I can see we've got a fairly large number of people already online. I'm looking to see if Brandon is here. Okay, Brandon, yes.
Hello.
Excellent. All right. I was hoping to meet a whole lot of people in person. It now has to be done virtually, but that's fine. So I'm going to hand over to Anoop, who will chair the first session of invited speakers, and he can introduce the speakers, and then we'll hand over to each speaker for their presentation.
Okay.
Steve, should I start?
Yeah, go ahead, Anup.
Oh, okay. Thanks, Steve. So welcome everyone to this session. I'm Anup Cherian. I'm a principal research scientist at Mitsubishi Electric Research Labs. So for this session, we have three fantastic invited speakers, Dr. Brandon Amos from Facebook Research, Ricky Chen from the University of Toronto, and Professor Chelsea Finn from Stanford University. So we'll start the session with Dr. Brandon Amos. Dr. Amos is a research scientist at Facebook AI Research. He finished his PhD in 2019 from CMU and has done several exciting works in differentiable convex optimization for deep learning. And today, Dr. Amos will talk about differentiable optimization for control and vision. So without further delay, I'll request Dr. Amos to start his talk.
Yes, thank you for the introduction. And
Sure.
Let me see if I can properly share my screen for this. Okay, can you see my screen and hear me okay?
Yes, that's fine. Yeah.
Great. I'll go ahead and get started then. So yeah, thanks, Steve and everyone for having me and for tuning into this session. That was a really good introduction to kind of like this broader space of deep declarative networks and differentiable optimization and implicit differentiation. And I guess in this talk, I'm going to go deeper into a few more of the general principles behind the ideas in this space. And then towards the end, I'll talk about some of the newer work that I've been doing, mostly in the control space. So the rough division of this talk is that I'm going to try to spend about 15 minutes on this first part of differentiable convex optimization, which I guess in the framing of deep declarative networks is one specific way of instantiating a deep declarative network that has a convex objective and maybe convex constraints. And then in the second 15 minutes, I'll talk about applications of doing this in the controls context, where you can think about your controller as solving an optimization problem, and you can use that as a node in your computation graph. And I guess getting back to some of the motivation that Steve said is what do we actually want to do when we're modeling in machine learning or vision or controls or other contexts? And I think modeling is still a really large open question of what the best way of modeling for certain problems are, or for when you have some kind of data or when you have a lot of data. And I think one huge question that a lot of people are asking is it okay if we can just throw a big neural network at this data and just kind of hope that it learns the right thing? So I'm talking about the standard kind of set of like linear algebra that you can throw at all of these vision and RL and language problems. And this paradigm seems to work really, really good when we have a lot of data and when kind of like this setup kind of matches the kind of like the magic that like deep learning has. And so maybe in settings where we have a lot of data and where we know the right pieces of modeling tools to throw at it, and we don't necessarily care about interpretability or some kind of really out of distribution generalization, then maybe it's okay to just throw a big neural network at your problems. But I think that there are still a lot of cases where you have some kind of domain knowledge and you want to open up your model a little bit more than the traditional models give you, where you want to learn certain parts of something that's more structured. And this additional structure, this additional domain knowledge can come in a lot of forms. It doesn't necessarily have to come in the form of an optimization problem like what I'm going to be talking about. But I'll mostly talk about the optimization kind of like way of opening up your model and having specialized optimization components. And I guess as Steve prefaced here, is when I'm talking about optimization-based modeling in this context, I'm not talking about doing parameter optimization with some new optimization methods, or I'm not talking about gaining any new insights into optimizing the parameters of your model. I'm talking about having some kind of internal module or internal function where you can solve a sophisticated optimization problem that can represent a large class of operations, where you can kind of start opening up the what's like the computations in this optimization problem to kind of help understand what's being learned, or to add some kind of structure or domain knowledge to what you're learning. And I think that optimization is a really great way of adding structure to problems, because it very naturally captures a lot of reasoning problems that we might have about the tasks that we care about. So for example, outside of the learning or vision settings where this space is a bit nicer, like if you have a really good analytic view of the problem that you're trying to solve, for example, a lot of problems in computer science can be, or controls or other fields can be formulated as just an optimization problem with no learning. It captures this essence of reasoning in a really powerful way. And it starts breaking down when you're in fields like vision, or when you're in like language or other machine learning settings where you have one piece of data or one type or modality of data that you don't understand. And that makes it really difficult to put traditional optimization methods on top of that to do this kind of reasoning, because you can't really analytically describe the properties of your data. So the kind of push for optimization-based modeling is based around this idea that you have some structure that you think you might want to have in your problem, and you want to learn parts of that you don't know, like for example, the parts that are coming from vision or some other high-dimensional space. But you want to keep this kind of reasoning component internal on top of the learning that you're doing. And I'll quickly talk about some of the applications of this, or the more concrete applications of this in RL control, game theory, and beyond. But before I do that, I'm going to talk a bit more about some of the foundations and kind of just like other bits of intuition to kind of make the fundamentals here a bit stronger. So one kind of way of thinking about how you can learn hard constraints in your model is you can imagine your optimization problem has this knowledge of some constraint set or some kind of parameterized constraint set. And this piece could be over some latent part of your data. Like maybe you know that your data has some kind of latent hard constraints. Like maybe it's some kind of language or some kind of a visual task or some kind of properties of the world make you think that there is like some polytope or something that's underlying your data. And what's kind of nice about optimization layers is that you can directly parameterize this constraint set and you can learn it from data, which is what I'm showing in this example. So the blue polytopes and ellipsoids are the pieces that are the true polytopes that's perhaps underlying some data process. And the red polytopes and ellipsoids are showing what happens when you try to learn polytopes to match the data. So that's just one kind of intuitive example of how you can use optimization layers. A few other interesting ones is that you can also interpret some of the standard operations that we're already using as themselves solving optimization problems, or themselves solving convex and constrained optimization problems. And this is not necessarily a useful tool to improve our understanding of like the ReLU sigmoid or softmax, but I think it's a useful tool for understanding how convex optimization layers can help with modeling, because it captures this rich class of say, in this case, activation functions. And it kind of gives you a feel for how you could maybe extend beyond these cases. So just to quickly go over these, so the ReLU you can interpret as solving this optimization problem that I have at the bottom, where you are let me just change this color, where you at each point, say x is the input. At each point, you want to solve this quadratic objective, which I'm showing in the heat map here. And so say you have some x value of this point. You solve this quadratic objective, and you get out the identity function if you're in the positive part of the space, which matches the value in the positive part of the space. And then once you start going negative, you just kind of chop the solution to the non-negative worth-ins, and that gives you the flat part of the value. So that's kind of how you can translate what the value is doing into this differentiable optimization view. And one thing to keep in mind, or one thing that kind of comes up in the machine learning setting, is that we really care about computing derivatives through these operations. So, for example, the derivative of y star with respect to x. And this is really obvious how to do it in the normal value case, because it's just an explicit closed form operation. But in the optimization case, it's not clear a priori that you could get any reasonable derivative flow through the output of this argument operation into the components of the objective or the constraints. In the value case, it happens to work out. But there's not always a closed form solution to your optimization problem. Just to quickly go through these next two examples too, you can also look at the sigmoid as solving an optimization problem, where it's kind of the same idea, where you are projecting onto this the 0-1 box in this case, where if you kind of plot out this heat map or plot out this the objective, you can get a sense of how this works. So at each point, you solve this optimization problem, and turns out this entropy penalized objective gives you the sigmoid. And you can check that from essentially just differentiating this objective. The constraints aren't as important because you already have the entropy constraint here. And lastly, you can also do the same thing for the softmax, where the softmax is also just doing an entropy penalized projection onto the simplex. And you can also see this from taking the first order optimality of this optimization problem. And again, you have a closed form solution to this problem. And so the natural, I guess, generalization of these ideas is how do you handle arbitrary convex optimization problems that look like this, where you might not necessarily have an explicit closed form solution, and you're possibly also learning or parameterizing other parts of this optimization problem. So in these last few activation functions I showed, you typically just have this the inputs parameterized as the you're differentiating with just respect to the inputs, but you can also parameterize these layers and learn other parts that perhaps stay fixed, kind of like the polytopes I was showing earlier. And I guess the one trick to differentiating through these optimization problems is that you just you can use the implicit function theorem in a lot of cases. And the implicit function theorem says, okay, we have a function f which is defined as the roots of this g function, and we might not have a closed form solution to what f is, but we know what g is. And the implicit function theorem gives a way of computing the derivatives through f with respect to x in this way. And if you, I won't talk about this in too much detail, but if you think about what this is doing, is you can kind of imagine that it just has a good way of combining the derivatives of this g function along both directions that you kind of have access to. And this works under very mild assumptions. In most of the convex optimization cases, this is it almost always works. So I guess taking this piece, we can now take this and apply it to these optimization problems, or these more general optimization problems, to get the derivatives that we want for say like the machine learning setting. So if we start with a quadratic program, we have something like like this. So we're filling in now the objective with maybe some parameters that are kind of shaping the cost and also shaping the constraints of the objective, so or of the optimization problem. And the only thing you need to do to get to this point to differentiating is you need to convert it into an unconstrained root finding problem. And in this quadratic program case, we can do this through the KKT conditions directly, where you have essentially this mapping, or this kind of residual of the optimization problem, where you know that if you have some optimal primal dual point Z, then if you're at the 0 point, then you know you have a solution to the original optimization problem. And so now this is an implicit function, and we can just apply the implicit function theorem to differentiate through this with respect to the parameters that we care about, which instantiating it looks like this. Now generalizing beyond this class of quadratic programs, because not every problem is a quadratic problem, and it's definitely worth thinking about how to differentiate through more complex optimization procedures. I guess long-term, even non-convex optimization procedures or certain other more general classes. The only generalization I'll show in this talk is on conic programs, which kind of subsume a lot of convex optimization problems. So conic programs have this nice property where you can actually transform almost any convex optimization problem into the conic form that I have on the screen, where I'm writing it where in this case it has a linear objective. You'd also imagine having quadratic objectives or more general forms here, and you have this constraint where this mapping lies within some convex cone, where the convex cones can be some simple cones, like maybe it's just like this mapping is just zero. Or you could have like the free cone or these other more complex cones, like the second order cone, like this one, or a semi-definite or exponential cones. And you can take Cartesian products of cones. So these are really powerful representations of convex optimization problems, and the nice tools that we have for convex optimization, like CVXPy and this family of kind of languages that can transform optimization problems, it provides a really nice way of automatically transforming optimization problems into this conic form. And so now if you want to differentiate through the conic form, you essentially apply the same trick, where you just need to convert the conic optimization problem into some set of optimality conditions, which in this case comes from a slight change on top of the KKT system because of the conic constraints. But once you have that, then you also just apply the implicit function theorem and can easily get the derivatives that you want to have. And so now that we have this kind of like a toolbox or class of methods for differentiating through these class of convex optimization problems, we can think a bit more about applications. And there's definitely a lot of things that we could talk about here. I've left most of these applications out of this talk. So beyond like the hard constraints and projections that I mentioned earlier, I think there are a lot of interesting applications in game theory, or perhaps some kinds of economics, like either where you're finding equilibrium points or of games or of markets. In the control setting, which I'll talk about later, this can induce differentiable policy and control-based classes. In the meta-learning setting, there's quite a bit more to talk about than I have listed here. But differentiable SVMs are an interesting piece of meta-learning that you can do, where you can imagine just formulating the SVM like hyperplane fitting problem as solving a convex optimization problem. And also in the energy-based learning and structure prediction setting, if you have a convex inference procedure, you could, and that's something you can especially imagine differentiating through it. Even in non-convex inference procedures, you can also imagine differentiating through that in some other way. So I'll mostly I'll leave most of these applications out of this talk, but I'll focus on, I guess, one kind of more foundational one, and then I'll go deeper into this control part later in the talk. So I think one interesting generalization of this idea that you can project onto the simplex, and you can interpret the solution to that as the softmax. I think there's an interesting connection here to say vision and to other cases where you want to differentiate through the top K operation. And the way you can see this is that if you write out the optimization form for what the softmax is doing, is you can see that you can kind of interpret this constraint as saying find like the maximum, or find the almost maximum, like the vertices of the simplex are the like the maximum indexes of whatever you feed into this. And you can imagine generalizing this so that you have this polytope that now has k active elements at each of the vertices, rather than just having a single active element. And we can kind of visualize this to get a sense of what this looks like. So just quickly going through these. So this is showing the penalty service actually on top of these polytopes, which comes in this case from the entropy terms. So the sigmoid, it's this box, and the vertices of the box are every possible combination of the like multiple labels you can have active. The softmax is just the simplex, where the indexes are just every possible active index you could have. And now as you extend to the top K setting, so for example, this is the top 2 setting. If you have 3 input items, it's every combination of 2 elements that you can have from your set of inputs. And you can start visualizing this in higher dimensions as well, like I have here on this hypercube. So if you have k equals 1, then you just get back the simplex. And then if k is 2, then you get back this other polytope that actually is also the simplex in this case. And as you go beyond to higher dimensions, you start getting these kind of more sophisticated polytopes, where this is where you have 4 elements on the inputs, and you want to look at the space of 2 active elements. So that's the idea, that if you want to differentiate through the top K operation, you can just formulate it as this optimization problem and differentiate through this optimization problem. And I'll show an application of this in the control setting later in this talk. One last fundamental or foundational piece that I want to talk about is more on the implementation side of these methods. And it's that these methods do need to be carefully implemented. I won't talk about all of the details on the difficulties that come up here just for the sake of time, but it's quite challenging actually to efficiently implement these optimization layers. And I think at least in the class of constrained convex optimization problems, we're at a good point where practitioners can kind of just throw away all of the details about the simplistic differentiation stuff. And in this case, we can just use CVXPy or some other kind of domain-specific language for prototyping these new layers, where it gives you a nice way of writing a few lines of code to construct and instantiate these optimization problems. And it has the efficiency of the past implementations that we've had that handle nicely the batches of optimization problems and so forth. And internally, this is just going through the differential conic optimization problem I mentioned earlier with another few pieces. Definitely let me know if there are any questions on this part, since I've gone through kind of fast, so that we can get on to this next part of the talk on differentiable control and reinforcement learning, which it looks like I have 5 minutes left. So I'll just briefly talk about some of the motivations in this space. So I think one long-standing question in the RL community and in the controls community is how we should formulate our policies, and if we can just throw a lot of data or simulations at black box policies that just directly map from some states to some action that we take. And I think it makes a lot of sense if we have a lot of data and we can allow a lot of interactions allow for a lot of interactions with the environment, then a model-free reinforcement learning works pretty well. But I think in other settings, we do care about having some kind of more structure or knowledge about what's actually going on, about how policies are making decisions and how they're generating or potentially using future plans. And I think control is a good way of adding a structure, which is used in a lot of cases where you perhaps know the costs that you want to optimize on your system and you know how your system works. You can just formulate it completely as an optimization problem without learning. And then maybe when you start moving to higher dimensional systems and you don't know how your system transitions or you don't know the cost that you want to optimize, especially in visual-based robotics where your robot takes in vision as a state space, it's quite difficult to write out the cost of the controller that you would want to optimize that perhaps is beyond some of the goal-driven or goal-oriented cost functions. One issue, some more fundamental problem in this space when you're learning parts of your control problem or when you're learning components that are going to be put into a controller. It's something I'm calling we're calling the objective mismatch problem. And this problem comes from having a policy that's interacting with the environment and receiving responses from that environment. And the responses come in the form of state transitions and also rewards. And what people typically do, it's not always like this, but typically you would, if you don't know the dynamics of your system, for example, you would fit those with maximum likelihood to your observed state transitions, and you would then feed that back into your controller that induces some other policy. And what I'm calling the mismatch problem is, I think, really crucial and really a really hard challenge in the field is that if you fit your dynamics for maximum likelihood, it doesn't necessarily understand this like reward or it doesn't have any signal of the reward that it's actually inducing. And so you can run into these weird situations where maybe your environment has a lot of really irrelevant parts to it, but because you're fitting the maximum likelihood, then you're trying to put a lot of modeling capacity to these parts of the environment that don't matter at all for the reward that the policy is obtaining. And in fact, these complex parts of the environment can distract significantly from the reward. So I think there are quite a few solutions or proposed ways of mitigating this issue where I think differentiating through your controller is one way of thinking about kind of getting around this issue, because it allows you to directly inject knowledge of the reward signal into the learning of say, your system dynamics. So this kind of gives you this a replacement for black box policies in some settings. And you can just kind of plug it in anywhere you can plug in a black box policy. And skipping over most of the details for now, is that there are actually quite a few ways of instantiating differentiable controllers. This is one that we were doing a few years ago, is on differentiating through a chain of quadratic programs, where this is state of the art for a lot of optimization or a lot of controls problems where you kind of know that you have a low dimensional space. I'll skip over this slide. There's interesting connections to differentiating through LQR. And a second idea in this space is that you can also differentiate through these optimizers that generate sequences of samples rather than I guess like the other kinds of like unrolled optimizers. So instead of unrolling through gradient descent, you can unroll through optimizers like the cross entropy method that generate sequences of samples. And this is also nice because the cross entropy method is also a state-of-the-art controller for model-based RL. It looks like I'm at the time limit, so I'll just spend a few more one more minute just closing off. I don't have that many more slides. So yes, the differentiating through the custom tree method is actually easy if you just use the top K operation. And you can start applying it to these kind of more non-trivial systems where you can start fine-tuning and trying to fix the objective mismatch issue in some of these settings where you're generating these very long horizon predictions of your dynamics, like this cheetah. There's another interesting idea that's in the paper of how you can use this to exploit the solution space structure, which is kind of orthogonal to this objective mismatch issue. But I will defer this to to any future conversations we may have. So with that, that's all I had to talk about today. And yes, thank you for coming. Thank you for having me, to the organizers. And yeah, I look forward to the rest of the workshop.
Thank you so much, Brandon. It was an amazing talk, and it's very useful. I mean, I personally used OptNet for some of my projects, and it's awesome. It solved. I mean, it reduces a lot of complex things that you have to do, and it's very efficient as well. It's wonderful. We are running out. We've run out of time, so I'm not sure if there is a possibility of questions. But I think there is a. Maybe you can send. I mean, if there is a question, then maybe you can chat offline through emails, perhaps. I'm not sure if there is any direct way of doing it with this virtual platform, but yeah. So thank you so much again, and I look forward to talking to you sometime later in person. Yeah, thank you.
Yes, thank you. Bye.
Thanks, bye. So moving forward, so our next speaker for this session is Ricky Chen from the University of Toronto. Ricky is a PhD student working with Professor David Duvinod and is best known for his work in neural differential equations. He won the Best Paper Award at NeurIPS 2018 for his work on neural differential equations. And so today, Ricky will talk about tractably modeling with constraints using neural ordinary differential equations. So Ricky, yeah, you can start. Yep. Thanks.
All right. Thank you, Anup. Thank you for the introduction. Yeah, so hi, everyone. Again, Ricky, I'm a PhD student from the University of Toronto. I'm also supervised by David Duvinod. So I'll be talking about an approach to modeling with constraints, and I'll be discussing some of the follow-up works that were done by me and my peers at Toronto. Yeah, so in this talk, I'll first just sort of dive in and summarize what comprises a neuro-ODE, and then I'll discuss the intricacies of using these continuous time models versus their discrete time analogs. This will hopefully shed some light on some of the properties of neuro-ODEs, the type of constraints that they model implicitly, and ways to turn them into beneficial aspects. Then I'll be sort of diving deeper into highlighting the use of neuro-ODEs to construct tractable generative models, using specifically continuous normalizing flows and a more constrained but highly scalable variant called residual flows. Right, so just so we're on the same page, I just wanted to give a very brief intro into how ODEs work, how they can be numerically computed in practice, and the motivation behind their use as a modeling tool. So it's easiest to compare to a simple integral, where we parameterize the derivative of some quantity h as a function f of an independent variable t. So the goal is to find the function, a unique function h of t, that has this derivative and also passes through some initial value h at time 0. Right, so the simplest method is to basically just approximate the solution with a series of Riemann sums. So on the grid of t values, we evaluate f basically all in parallel, and then multiply by the step size delta t, and then sum these quantities up. So while the true solution can only be written as an integral, in practice we would typically just have to approximate with a finite sum. Now, solving an ODE amounts to exactly the same problem, but now the derivative of h is expressed not just as a function of t, but also of h itself. This means we can't easily evaluate f because that would require having the solution to h already. So instead, as an analogy to the case of simple integration, we also start with an initial value for h at time 0, which lets us compute f at time 0. Right, so the idea is that we then need to sequentially build these Riemann sums. Right, we iteratively approximate h at the next time value, and I use this approximation to evaluate f, which lets us compute the next Riemann sum. So we can't do these Riemann sums in parallel anymore. Now the result is what is known as an Euler discretization. So in the limit as the step size goes to 0, this would recover the true function value. Now, this extra inconvenience of expressing the derivative as a function of the state h itself means that we can model a much more flexible family of amortized functions. Whereas with a simple integral, the initial value only affects the value of h as an additive constant. In an ODE, the state h depends non-linearly on the initial value. So this ODE parameterization is also often more natural. So in many domains, the change in the state of a system doesn't really depend on the time itself, but it depends more on the current state of the system. Right? So this type of parameterization is also more generalizable to unseen time values. So there's this often mentioned connection between residual networks and ODE solutions. There were early works by E and Haber and Ruthodo discussing the use of concepts from dynamical systems and applying them to improve residual networks. Now, the hidden units in a ResNet follow this formula, where each layer has a residual connection. So you apply F on the state itself, and then you just simply add it to the input. Now, this can be interpreted as a specific way of solving an ODE where F is a differential equation, specifically with a step size of 1 and the Euler discretization. Now, from this viewpoint, we can view a neural ODE as the infinitesimal limit of a ResNet, where the step size goes to 0. Okay, so next I'll talk about some subtle differences between solutions of ODEs and fixed step size discretizations, such as ResNets. And we'll find that neural ODEs are actually a more constrained class of models, but this leads to some very interesting applications. All right, so how expressive can a neural ODE be compared to just directly parameterizing the discretization scheme? And it turns out that ResNets are more expressive than ODEs, and this can be easily seen from an example. So suppose we want to fit the function, just a 1D function x squared, and we do this by taking x, specifically x as the initial value at some time h0, and then taking the state h at t for our prediction for y. So this is a trained neural ODE, and we can visualize the trajectories modeled by multiple inputs. So on this graph, t is the y-axis, and then h is the x-axis. So at the very bottom is what x is, and then at the very top is our prediction for y. So we see that while the neural ODE can transform positive values of x to x squared, it fails to transform any of the negative values. And this is due to a simple property of ODE solutions, that the trajectories conditioned on different initial values can't ever meet or cross each other. This is because the solution of an initial value problem is unique. And this uniqueness property is satisfied as long as f is Lipschitz continuous. But if we parameterize f as a neural network, as in the case of neural ODEs, it's basically always Lipschitz continuous, theoretically. Right? Because otherwise we wouldn't be able to apply gradient-based optimization to train neural nets. Okay, so this uniqueness property means that the mapping from h at any time to h at another time, this mapping is always a bijective mapping. So on the other hand, a residual network, or really any coarse discretization of an ODE, is a model that's not always constrained to always output bijective transformations. And as such, it can easily learn this x squared function. In fact, it actually learns to merge both the positive and negative values in the first residual block. But we know that no ODE solution could ever model this, because this would imply that the solutions must cross at some point between the first and second residual blocks. This little experiment basically just shows that there exist functions that, while they look like discretizations of some underlying ODE, these functions don't actually correspond to the solution of any ODE. But because of this, the discretization, or the ResNet, is more expressive as a modeling tool. And ODEs model a more constrained set of functions. All right, so the implementation-wise, really the only difference is the use of an adaptive discretization scheme to ensure that the ODE is actually being solved correctly. Right? So we still parameterize f in both cases. During the course of training, the ODE, or rather this function f, becomes more and more complex. So if the ODE solver is not flexible enough, we won't be able to properly constrain our models. This is really only the case for fixed and coarse discretizations, but whether a discretization is coarse depends on how regularized f is. So if f changes significantly within a small interval, then the step size needs to be small enough to not miss that information. In this case, the solver we use acts as an arbitrary to the objective that we want to optimize. Its job is to ensure that the model remains within this constraint set, which often opposes the objective itself. So as a quick remedy to this, just to mention this briefly, the augmented neural ODEs paper by Dupont et al. Proposes basically just adding extra dimensions to the state. This still retains the continuous time properties, so your trajectories are still smooth, and the final state can still be used to recover the initial state. So that mapping is now, it's still injective, it's just not surjective. And furthermore, some recent works, particularly by this one by Zhang et al., have proven a sort of universal approximation theorem that states by adding just one extra dimension, neural ODEs can represent any continuous function. All right, so to highlight a few applications before delving deeper into tractable gender modeling, one motivation for ODEs was to be able to model irregularly sampled time series. So ODEs are the natural fit because we can compute the solution at any time value, and we don't have to adhere to a specific time discretization as would be in the case of like recurrent neural networks. So one of our follow-up works was to augment recurrent neural nets with the ability to interpolate its hidden state between observations. This was motivated by the presence of medical data where observations of each patient came in the form of tests which were done at very odd intervals. To efficiently handle this kind of data, we proposed modeling changes in the hidden state between your observation times. So some existing works used an exponential decay to create a sort of continuous time recurrent neural net. But this is really a special case of a very simple linear ODE. So we generalized this to using neural ODEs, and we note that this ODE transformation wouldn't lose any information about the previous hidden state because ODE solutions, again, are invertible. But they can still represent changes to the representation itself. So at observations, we can still use any RNN update formula to update the hidden state in a discontinuous fashion. Another benefit that some research groups have been pursuing is the modeling of dynamics with specific constraints. So here you would constrain the dynamics function itself. Specifically, the Hamiltonian and Lagrangian neural nets model physical environments that satisfy a conservation of energy. Finzi et al. Use transformations that are equivariant to Lie groups to design dynamics that conserve momentum. And then Reisi et al. Have papers that construct physics-inspired architectures. This one in particular tries to mimic fluid, incompressible fluid simulations. There are some interesting applications when certain constraints are known regarding the target domain. And the neural ODE approach lets them train complex models within the confines of such constraints. And these constraints are typically easier to parameterize in the form of an ODE. And I think in the future there will likely be more applications outside of physics. ODEs are quite prevalent in fields such as like economics, finance, epidemiology as well. Okay, so that was a brief general overview of some use cases for neural ODEs. So from now on, I'll start going into more depth on tractable gender modeling with applications to density estimation, training scalable gender models on, for example, images. Right, so one promising application of ODEs is to construct what is called a normalizing flow. This describes a family of tractable probabilistic models defined by a neural network generator. So central to normalizing flows is the use of an invertible function that acts as a mapping between some latent space Z and the data space X. Typically, the distribution in Z is chosen to be very simple, so you can efficiently sample from it and you can efficiently compute its probability density. But with a very complex transformation, Z can still be transformed into any distribution with the same dimensionality. So due to the invertibility of this mapping, the probability density function can be exactly computed at X, unlike a generative adversarial network. So this tractability generally makes normalizing flows more applicable to a variety of scientific domains. And I'll be discussing a subclass of these models called continuous normalizing flows, or continuous time normalizing flows, which was first discussed in our original neural ODEs paper. So to describe this, I'll use a very simple 1D example. The problem setting is quite simple and it's quite general. So we just have a bunch of observations, and we want to fit a potentially very complex distribution. We can parameterize this potentially very complex distribution by starting from a base distribution and then learning a transformation that's parameterized by a neural ODE. This distribution and the transformation are really the only two things that we explicitly parameterize. The idea is that the neural ODE redistributes and then transports mass from the base distribution at the bottom in order to define a distribution on X. And the relationship between the density in Z space and X space is given by this formula on the right that requires integrating over the divergence of F along the trajectory from Z to X. Normalizing flows basically have normalizing in their name because we always have access to automatically normalized density functions. All right, so what this equation lets us do is basically build powerful density models in high-dimensional continuous space. And it also provides us with a generative procedure for sampling from X. Right? So we can basically just sample from Z and then transport the sample into X space. So instead of a crude drawing, let's see if this works. Oh, there we go. Okay. Right. So this is my crude drawing. This is a neat GIF that was created by Jesse, who co-authored the neural ODEs paper. So at the bottom is a simple Gaussian, so standard Gaussian, and then at the top is that transformed density function. You can see from this visualization that the learned ODE is slowly transporting mass from a single mode into multiple modes. And in fact, each horizontal slice is a properly normalized density function. A continuous normalizing flow essentially defines an infinite set of distributions, one at each value of t. And without additional regularization, these intermediate distributions are really free to be whatever they want. But in fact, they can be regularized so that the intermediate distributions are more meaningful as some sort of interpolated distribution, which I will discuss in a bit. So first I'll talk about this a bit. So in practice, the divergence of a neural network, so we're parameterizing F as a neural network, and the divergence isn't cheaply computable. The divergence is the trace of the Jacobian, trace being the sum of the diagonals, and the Jacobian is the matrix of first order derivatives. So in the follow-up work by Graffel et al., we propose using the Hutchinson's trace estimator to stochastically estimate this integral over the divergence. The key insight here was that this trace estimator only requires vector Jacobian products, which are easily computable in automatic differentiation frameworks. It's typically implemented in most deep learning libraries. So this helped us scale continuous normalizing flows to actually high dimensions, as I mentioned it, to small images like MNIST and CVPR. Okay, so going back to regularizing the trajectory, some recent works have made a connection between continuous normalizing flows and solutions of optimal transport. Optimal transport essentially chooses the shortest and straightest path from Z to X, but this is typically done in a non-parametric fashion where you have some samples from Z and some samples from X. So Finlay et al. And Toin et al. Proposed various regularization methods that, when applied, can steer the model towards learning optimal transport solutions. These regularizations essentially involve regularizing the Jacobian norm of F in some form. And also on the left is a diagram from Finlay et al. Where they show that the learned paths can be regularized to be straight, recovering a parametric solution to optimal transport. They also showed that this type of regularization can significantly reduce the required amount of compute for solving the neural ODE, implying that these solutions are less complex. And on the right is a figure from Toin et al. With the same idea. So they showed that the base continuous normalizing flow learns curved trajectories, but with their regularization method, it approximates optimal solutions, optimal transport solutions. Right, so Toin et al. Applied continuous normalizing flows in an interesting setting. So they used them to model cell dynamics of a developing human embryo system. So multiple observations were made, but only at very infrequent intervals of a few days. And so without explicit knowledge of which cells move to which location, this is essentially an unpaired problem where you have to figure out what the exact cell dynamics are. So the flow model learns how these cells transition across time. And since they observe multiple time values, the model can learn smoother and more generalizable transitions than optimal transport, which would actually only give you piecewise linear trajectories between the observed days. So once learned, the model can be used to perform interpolation to impute cell states at unobserved times. Another work by Young et al. Applied continuous normalizing flows to learn distributions over object shapes using a fully general point cloud representation. So for each class of objects, for instance here, a plane, a chair, or a car, they learn a latent variable that represents the shape, and then condition on this latent variable a continuous normalizing flow, then learns how to map samples from a Gaussian distribution into that desired shape. So this work just nicely shows the potential for using ODEs to learn complex distributions over point cloud representations. Okay, so next I'll talk about residual flows. So these are a much more scalable class of normalizing flow models that are sort of related to continuous normalizing flows, but they don't require solving a complex ODE. They don't require using a complex ODE solver, and they can simply use the Euler discretization, so they're kind of like a ResNet. So previously we discussed that because the function f can become arbitrarily complex during training, it's necessary to make use of an adaptive ODE solver that can adapt to the changing complexity of f. In practice, this usually amounts to choosing smaller and smaller step sizes as training goes on. Now, it turns out that if we explicitly constrain the set of functions that f can learn, then we can actually get away with using large fixed step sizes. We can show that if the Euler discretization, if we use the Euler discretization, the step size and the Lipschitz constant of f need to be in an inverse relationship. So without loss of generality here, we're always going to choose a step size of 1. This means f simply needs to always be Lipschitz less than 1. So based on this, we constructed invertible residual networks that have the same functional form as a standard ResNet, but it's constrained to always be bijective. And this visualization on the right shows that the standard ResNets might end up learning reflections in the middle, while invertible ResNets are constrained to never cross paths. All right, so once invertibility is satisfied, we can again use the change of variables formula to create a normalizing flow to create a tractable generative model, right, based on residual networks. By doing so, we actually obtain an infinite series, which is shown in red. This is the likelihood of your output. So written in this form, exact computation would be basically infeasible, as that would require infinite compute. Right? But this formulation of the log density opens up the possibility of using efficient estimation methods. So you might notice that there's a trace inside the infinite series, so we can use the trace estimator. But the main problem is this: how to compute this infinite sum. So the approach we take is quite general, and it's actually it's appropriately named the Russian roulette estimator. So here we do require that the infinite sum converges absolutely. And what I'll describe is actually quite a general approach that can be applied to estimate solutions of implicit problems, solutions of any limiting quantity. So maybe this can be your takeaway from this talk, even if you don't particularly care about general modeling. Okay, so we'll estimate this infinite series, delta k, one term at a time. So suppose we always estimate the first term, and then we flip a coin with probability q, and if it's heads, interpret it as a success or the value 1, we'll stop evaluating any more terms. Otherwise, we just keep evaluating. But if we continue, then we need to upweight the remaining terms, infinite number of terms, by a factor of 1 over 1 minus q. This is essentially because when we take the expectation, this reweighting cancels out with the probability of the outcome. And the result is just a very simple unbiased estimator. But something very interesting has happened here. So in computing this estimator, there is now a probability of q that we only need a finite amount of compute. But this estimator still has a non-zero probability of requiring infinite compute. So to take this even further, we can apply this trick over and over again to the remaining terms, sampling a new coin toss for every outcome that we have to continue. So we can do this. So we can obtain an estimator that uses finite compute with probability 1. And we basically just need to apply this trick infinitely many times. So instead of doing that, we can actually sample the coin tosses we can reparameterize this estimator to basically sample the first successful coin toss. And this will be a distribution over the natural numbers. Right. For every term that we compute in this sum, we only compute it because we failed k-1 coin tosses. So we need to weight these terms appropriately by that probability. And then the final unbiased estimator, when we apply it to residual invertible resonance, so the final unbiased estimator for this log likelihood uses two sources of stochasticity. So one is from the trace estimator, shown in blue, and then the other one is from this Russian roulette estimator, which is the one in orange. So we call this a residual flow because now it's basically a resonance, but it's also a normalizing flow model with one constraint, which is that the Lipschitz needs to be less than 1 for every residual log. So this unbiased estimator is also actually very efficient in practice. We specify P of n as a shifted geometric distribution that only has an expected compute of only 4 terms. And the geometric distribution has a very light tail. So we sample large values. So the chances of sampling a very large value of n is extremely small. All right, so actually another way, another way to approximate this log P of y is to simply always truncate at a fixed n. Right? But this is a biased estimator because it doesn't take into account any of the terms that are larger than n. So here's a comparison between training using that unbiased estimator with the Russian roulettes and just training using a fixed truncation at some n equals to 10. So the biased estimator used here during training, it's the red dashed line at the very bottom. It converges to something that's less than 1 base pair dimension. So base pair dimension it is a unit of the negative log likelihood. This is something we want to minimize. But the actual log likelihood was actually something that's closer to 10. Closer to 4. This is something we used the unbiased estimator to compute. And this log likelihood doesn't actually converge at all. This is not an effect of overfitting to the training data sets or anything like that. It's an effect of overfitting to the bias in the estimator itself. So in contrast, by using our unbiased estimator, the training is quite stable. It's the blue lines. And we can reliably train the model without having to worry about any sort of bias. So one potential downside of this estimator, though, is the variable compute and the variable memory cost. Variable compute isn't really a big deal because the expected compute is still constant throughout training, and the variance in walk-out time per iteration is actually quite small. But the variable memory is difficult to deal with because the maximum amount of memory required during training isn't known. This is because there's always some probability of sampling a large enough n and then suddenly running out of memory unexpectedly during training. So to remedy this, we use a different but equivalent gradient formulation. So we can first rewrite our estimator to emphasize the gradient path. So the constants are all grayed out, and then we just set them aside. If we estimate the log likelihood like this, and then backpropagate through the estimator, right, through the solver of the infinite series, we need to backpropagate through every single term in that series. This implies that we need to keep all the terms in memory. So the memory cost scales with n. Alternatively, we can actually analytically differentiate the original infinite series and then formulate the gradient as an alternative Newman series. We can then still apply the same unbiased estimator tricks to obtain an unbiased gradient estimator. This is a similar trick to the adjoint method for backpropagating through ODE solutions or the implicit function theorem for backpropagating through fixed point solutions. Essentially, we manually derive the gradient as an alternative formulation instead of backpropagating through the solver itself. We can then apply the same tricks to estimate this infinite series that converges to the gradient. So the biggest advantage of this estimator is that now we don't need to backpropagate through the estimate series. So we only need to backpropagate through a single Jacobian term, which is weighted by this estimate series. Okay. So do you understand the impact of this gradient estimator? This plot shows, I think I'm running out of time. Yeah, okay. So this plot shows the amount of memory that would have been required if we were to compute 10 terms of the infinite series. So the summary is basically, if we don't use the unbiased, if we don't use the alternative gradient estimator, that would be the blue line, and then that would basically be intractable if we try to scale to larger models. So the combination of a few tricks, including the gradient estimation, basically allows us to train very large models with as small amount of memory cost as possible. The quick summary for visual flows is that this invertible resonant architecture constrains the dynamics function, and then that lets us use a fixed discretization. This also translates to a fixed compute cost, whereas with an unconstrained F, we would have had to use adaptive solvers that typically increase in compute costs as F becomes more complex during training in the form of a neuro ODE. We also have memory efficient gradients for scalable training. I'll spare you the table numbers, but essentially we just scaled up to large images of 256 by 256 using, so this is all trained using the very simple maximum likelihood training objective. This was also trained using smaller models compared to previous normalizing flows because residual blocks are more expressive than with like a coupling block. Right, so the brief one-line summary, one-line takeaway is simply to don't be afraid to take limits. There are existing tools that can efficiently compute or efficiently estimate these limiting quantities. So using limits in your model or the objective is actually more tractable than you might think. So an ODE perspective also helps to introduce new methods that are like simple or yet flexible with a wide variety of applications. And I think this ODE formulation can encourage the use of deep learning in other scientific fields in the future as well. That's all. Thank you for listening.
Thanks, Ricky, for the enlightening talk. So we have time for a few questions, maybe one or two questions. So if you have a question, can you send me a chat message, and I'll give you the turn to ask a question. So Steve has a question. So Steve, do you want to unmute yourself and ask a question?
Sure. So thanks, Ricky. That was a great chat. Great talk. So I just had a question about the variance of your estimator. So it's unbiased. So you know on expectation you're getting the right estimate of the gradient. But how widely off are you on any particular instance? And does that really make a difference given that we sort of run stochastic gradient descent anyway, which is sort of adding its own variance?
Yeah, so I guess the nice thing about stochastic gradient descent is that it still works even if you have a very large variance gradient estimator. So one nice thing about this particular application of the Russian roulette estimator is that so we might not see it here, but basically this infinite series converges extremely fast, and this is because we explicitly constrain the Lipschitz of F to be less than 1. So that means this Jacobian is always less than 1. This or the trace of the Jacobian is always less than 1. So the spectral radius is actually very, very small for this infinite series. And that means we don't actually need to see too many terms, right, with large n's. And the stochastic estimator's variance depends on the convergence rate of the infinite series itself. So the variance is actually quite small, or manageable at least.
Cool. Thanks.
Okay. Thanks, Ricky. And so we have run out of time, and so let's thank the speaker. I'm not sure if this is going to be a big noisy setup, but we clap the hands. So our next speaker for this session is Professor Chelsea Finn. Professor Finn is an assistant professor at Stanford University. She has received several prestigious awards, including the SCM Doctoral Dissertation Award in 2018, and is most famous for pioneering the idea of meta-learning into mainstream machine learning and robotics. Today, Professor Finn will talk about meta-learning beyond few-shot classification. So, Professor Finn, you can go ahead. Thanks.
Great. Thank you for the introduction. So today I'll be talking about something that's a little bit different than what Brandon and Ricky talked about. Specifically, I'll be talking about meta-learning. And to motivate meta-learning, when thinking about how we might build generalizable models that can operate in the real world, I think we're often in a situation that looks like this, where our desired test distribution is much broader than the distribution of data that we may have data for. For example, in robotics, one of the fields that I work in, your trained distribution may be a lab environment, and your desired test distribution may be much broader, such as the real world, where you may encounter many different spatulas or many different kinds of environments. Or in computer vision, maybe your training distribution is ImageNet, and again, your test distribution is the real world, where these classifiers may not perform well across the board. So how might we try to extrapolate beyond our training distribution if we have trouble broadening our training distribution to the extent of what we'll be seeing at test time? Well, one way to do this is to try to build in structure into your model so that it can leverage that structure and generalize, use that structure in a way to allow it to generalize further. For example, you could build in compositional structure or symmetry like equivariance into the model to encourage it to generalize. Convolutions, for example, are one way to build in symmetry by saying that that data is translationally equivariant. Then the key question is, how do you actually build in the structure? One very natural approach is to try to build it in by hand. This is very natural because it seems like we're very good at generalizing, so maybe we can transfer our knowledge to the model. But I'd argue that we're actually really bad at building in the structure into models, just like we're really bad at building feature detectors. And we've seen this with kind of the history of computer vision when the performance on ImageNet got substantially better after the introduction of deep neural networks. So while we're really bad at building kind of feature detectors and building in structure, we are really good at learning from data. And so the motivation behind meta-learning is, can we learn structure from data and then transfer that structure to new tasks such that we can generalize with very small amounts of data? So how exactly does this work? I'll briefly overview how meta-learning works, and then I'll talk about some of the challenges and some of our recent work that really pushes the boundaries of what meta-learning can do. So the way that meta-learning works is we may want to be able to learn from a very small amount of data. And one kind of very classic example of meta-learning is this few-shot classification problem, where we may be given one example of 5 different classes, as shown here. This is our tiny little training data set. And we want to be able to learn from this training data set such that we can classify new test examples, as being among one of the 5 classes shown on the left. Now, of course, if we train from scratch, this is completely impractical to be able to solve from only 5 data points. But what we can do is, if we have image data from other image classes, we can structure that data in a way that prepares us for this few-shot classification problem at test time. We'd essentially structure those other image classes into mini train sets and test sets, and across these training classes, learn how to learn from each of these small data sets in a way that allows us to generalize to new test inputs. And then once we do this meta-training process across many different tasks, then at meta-test time, given a new task with new image classes, we can effectively solve the problem. Essentially, meta-learning is learning how to learn from small amounts of data such that you can generalize to new tasks. And in this example, the tasks are image classification tasks, but they could also be other machine learning tasks like reinforcement learning, imitation learning, and so forth. So that's roughly how the meta-learning training setup looks like. And one approach that kind of fits within the theme of this workshop is to embed a learning process, an optimization process, inside the process of learning from our small training data sets. And in particular, we might start with some neural network, take our tiny training data set, run an optimization on this data set to get a new neural network, and then optimize this entire process such that when given a new image, you can output the correct label. Essentially, we're training these neural networks, training this optimization process, for example, the initialization or other aspects of the optimization like the learning rate, such that you can learn from smaller amounts of data. So this is kind of the key idea behind meta-learning. And one algorithm that I developed back in 2017 is model-agnostic meta-learning. What this algorithm does is that it learns a set of initial features that are particularly well suited for fine-tuning with small amounts of data, such that with one or a few gradient steps, you can generalize effectively. Okay, so that's a brief overview of meta-learning. And while meta-learning allows us essentially to lift kind of training and generalization from data points to tasks, we still need to make this assumption that the task distribution that we're meta-training on is the same as the task distribution that we are given at test time, or at meta-test time. And we often find ourselves in a situation where actually designing many of these tasks can be pretty challenging, and our desired meta-test task distribution, the task we want to be able to generalize with small amounts of data, is broader than the task that we are meta-trained on. And in particular, often we want to learn new tasks that are related to the meta-training tasks, but not necessarily draw an IID from the meta-training distribution. To think about this problem, we need to think about the word related. Like, how do we actually define whether a task is related and so forth? To do so, we're going to consider tasks as being related if they share a certain structure. And in particular, in the first part of this talk, we're going to be talking about structure that corresponds to equivariance or invariance. And we want to see if we can discover equivariant or invariant structure via meta-learning, essentially if we can discover symmetries in the data, and then transfer that structure to new tasks to be able to kind of transfer more effectively to tasks that may be a little bit different. And in the second part of the talk, we'll see if we can try to adapt a distribution shift in the data, specifically using the structure recovered by meta-learning. Okay, so first let's talk about whether we can discover equivariant and invariant structures via meta-learning. Now, the first natural question here is, does meta-learning already do this? And in particular, does the MAML algorithm, the model-agnostic meta-learning algorithm, already allow you to discover a structure and use that when transferring to new tasks? Now, it's worth noting that MAML can learn initial features, an initial neural network that has a certain equivariance, simply by encoding that in the weights of the neural network. However, the gradient descent step may not actually preserve that equivariant structure. So while the initial features may be equivariant, the features learned in the second step may not be equivariant. Or the features learned after the gradient step may not be equivariant, may not share that structure. And so what we're going to try to do here is we're going to see if we can essentially decompose the weights of the neural network into a particular equivariant structure that preserves things like translational equivariance or rotational equivariance and so forth, decompose that from the underlying parameters of that network. Essentially, if we could do this, basically, we can update only the parameters in the error loop and retain the equivariance across the update step. Okay, so this may be a little bit abstract and vague, but hopefully it'll get more clear as I go on. And the first thing we want to look at is how our equivariance is actually represented in neural networks. And to do this, let's look at an example. So all of us should be pretty familiar with how convolutions work. And in particular, here's a visualization of a 1D convolution layer, where the input X is convolved with a filter W to produce the output Y. And the way this works is you take the dot product between the filter and the input, and you slide the filter across the input in order to produce the output. Now, this is one way to represent a convolution layer as this filter that you're sliding across the input. But another way that you could represent it is actually using a fully connected layer. And the corresponding fully connected layer looks like this, where the weights of the filter are actually repeated across the fully connected matrix, and the remaining entries are all 0. And then this basically corresponds to the identical function as the one on the left. Okay, so now that we have a mechanism, and actually it's worth mentioning that you can also do this with other things like other than convolutions, such as other kind of rotational equivariant functions as well. You can always kind of construct a fully connected layer that has the same sort of equivariance as that original function. So now that we have this visualization, we can note that basically what convolution corresponds to is a certain weight sharing pattern and a certain weight sparsity pattern, where ABC is shared, like different parameters of this fully connected matrix are shared in different parts of the matrix. And so what we're going to try to do is we're actually going to try to reparameterize this fully connected matrix such that part of it is representing the weight sharing pattern and another part of it is representing those parameters, the ABC parameters. And in particular, the way that we can do this is we'll have our parameters shown in yellow and green, and this is just a really simple example with 2 parameters. And then we're going to represent this sharing matrix as U. And this sharing matrix is basically saying for each parameter in our fully connected network, for each weight in our fully connected network, which parameter is it going to use? And when we multiply this matrix times this vector, we'll get a vector of weights, and then we'll reshape that into a fully connected network. Essentially, this is a way to reparameterize, in this case, a fully connected layer, just a matrix, as something that is composed of a smaller number of parameters. Essentially a way to represent different ways of sharing parameters. And it turns out that we can actually theoretically prove that this reparameterization can directly represent decoupled equivariant sharing patterns and filter parameters. And we can prove this for all group convolutions for finite groups G. And this is pretty nice because this means that we can actually, this is a means to essentially decouple certain kinds of structure, in particular equivariant and invariant structures, where invariance is actually a special case of equivariance, and decouple that from the underlying shared parameters themselves. Note here in this example, the sharing matrix is discrete, it's only zeros and ones, but you can also represent this with continuous values to represent other forms of equivariance. Okay, so with this kind of decoupling, or with this kind of reparameterization of a fully connected layer, what we can do is essentially, when we're meta learning, the inner loop can basically only update the parameters V, such that when you take kind of your weight matrix W is represented by U times V. When you take your inner loop loss, you can backpropagate that only into V, keeping U fixed, such that after the gradient update, the equivariance in U is preserved, it's fixed, and the underlying parameters are what's updated for the data. And then in the outer loop, we'll learn both the equivariance U as well as the initial parameters V. So essentially, this is allowing us to learn certain equivariance patterns that we assume are fixed across all of the tasks in our meta training set, and therefore allow us to kind of learn that and preserve it for all of the tasks. Okay, so we refer to this as meta-learning symmetries by reparameterization, MSR, essentially kind of a reparameterized version of MAML. And with this method, we wanted to answer a few questions. Our first hypothesis is that with this approach, if we have translationally equivariant data, it should be able to discover the structure of convolutions. And so what we did is we generated synthetic data from a variety of different translational equivariance data. It was data that kind of had a vector of inputs, a 1D that is 1D, then a function that has a 1D translational equivariance and produces an output. And with this data, we ran the previous approach that I just described, as well as MAML with a fully connected network, a locally connected network, and a convolutional network. And what we found is that when we were measuring the mean squared error for these for new meta test tasks, MSR was able to achieve performance that's comparable to MAML with convolution layers, even though MSR was starting with a fully connected network. And of course, MAML with fully connected networks and locally connected networks performed worse than MAML with convolution networks because they don't have this equivariance. And further, we can show that we can actually visualize the kind of what it learns, the matrices that it learns, and it learns something that exactly looks like that matrix that I showed earlier with the particular sort of translational equivariance, with the weights copied over the matrix. Okay, so this is the first question we asked. The second question we wanted to ask is, can we actually discover something better than convolutions in situations where our data isn't exactly translationally equivariant? And so to do this, we generated synthetic data first with partial translation symmetry. In this case, the partial translation symmetry was a locally connected network where there was a large amount of sharing between the filters in the locally connected network, but not all of them shared. So we considered either one filter that shared for all of the locally connected network, which corresponds to convolution, as well as 2 filters that are shared across the locally connected network, and 5 filters that are shared across the locally connected network. And what we find is with 1, 2, and 5 filters, MSR is able to discover that symmetry, basically a symmetry that works well and achieves low mean squared error, whereas convolution is able to do well, MAML with convolutions is able to do it well in the k=1 case, but isn't able to do well in the 2 and 5 case because convolutions is making too strong of an assumption about the symmetry of the data. And likewise, locally connected and fully connected are making too weak of an assumption about the symmetries in the data. The next thing we want to look at is data with translation that is translationally equivariant, rotationally equivariant, as well as reflection equivariance. And in this case, we actually initialized MSR with a convolution network instead of with a fully connected network. And we found that MSR was able to outperform MAML with convolutions by learning this stronger equivariant structure. Okay, so this is pretty cool. And so far, this was all on synthetic data. The last experiment we wanted to look at is if we can learn symmetries from augmented data. Essentially, if we can learn in a way that essentially builds or bakes in the augmentation into the architecture or into the neural network itself. It basically bakes in those symmetries into the architecture. And so to do this, we have a very simple algorithm where we have a set of meta-training tasks, any sort of meta-learner, and a data augmenter. And for each task, we split it into a train set and a validation set, augment the validation data points, and then construct our new tasks using the original train set and the augmented validation set. And so what this is going to do is it's going to train it such that after it's seen original images in the training data set, it could generalize well to augmented images. Essentially, we're trying to bake in the data augmentation into the update rule or the architecture that the meta-learner acquires. And what we find is when we compare MSR to MAML, almost no inner loop, a variant of MAML that only trains the last layer as well as prototypical networks, MSR is better able to capture these kinds of equivariances in its learning process compared to these prior works. Okay, cool. So we're pretty excited about this in the sense that I think it provides a framework for understanding the interplay of features and structure in meta-learning. And specifically, it decomposes those two things, at least for equivariant and invariant structure, such that we can control which are being adapted in the inner loop and which are being shared across all tasks. Okay, so far we've talked about learning symmetries. And the goal of using kind of structure and compositionality and equivariance is actually to get better generalization. And we showed one form of better generalization previously where we wanted to generalize to augmented data. But we also want to study a setting where we may have distribution shift from the training data to the test data. So can we adapt to distribution shift using the structure recovered by meta-learning? So to do this, we first need to think about what kind of distribution shift we'll be considering. In this next work, we're going to be talking about group shift. And in particular, we're going to build upon previous work on group robustness that considers there's this categorical group variable Z that may be things like gender, race, some background scene, etc. And we're going to be assuming that we're going to know this group variable during training for each of the training data points. Then we're going to assume that our training data is drawn from this distribution and our test data is drawn from this distribution. So P of X and Y given Z is going to be the same between training and test time, but this underlying distribution over Z may change. And this can capture situations such as label shift and most forms of covariate shift. Now, one very popular approach for handling this kind of distribution shift is called group distributionally robust optimization. And essentially what this tries to do is to form an adversarial distribution Q of Z and optimize for the worst case distribution over Z, such that when you're given, maybe at test time you're given a minority group, such as a minority race or a minority gender, you don't want to sacrifice, you want to get kind of the best worst case performance, even if that group is heavily underrepresented in the data. And this approach can enable very robust solutions to these kinds of groups. It's also less pessimistic than adversarial robustness, which may try to essentially be robust to really any sort of perturbation of the image. The downside, though, is it is still somewhat pessimistic and often sacrifices average or empirical group performance in the process of being robust. So what we'd like to do instead is try to adapt instead of aiming for simply robustness. And in particular, we assume that we have a set of unlabeled images that represent the part of the distribution that we're in at test time. And our goal will be to try to essentially adapt to that sub-distribution. And we'll call this, and so we're assuming essentially that all of our test inputs at test time are available in a batch, all of our unlabeled test inputs, and these are all part of one sub-distribution. And we'll refer to this as adaptive risk minimization instead of empirical risk minimization in the sense that we're going to be adapting at test time to the part of the distribution that we're in. And then the algorithm that we'll use will first construct subdistributions of the training data and then train for adaptation to those subdistributions. So the way this will work is at training time, we'll have all of our images, their corresponding labels, as well as their corresponding groups. We'll construct many different distributions from the group data such that we can sample a subdistribution and then adapt that subdistribution. And each of these subdistributions will be constructed using group information. Depending on the application, we'll construct things in a slightly different way. We may construct a uniform distribution over different proportions of groups, or we may have a subdistribution correspond to a group itself. Okay, so how do we actually train for adaptation to unlabeled data? For this, we need to essentially build a meta-learning algorithm that can adapt to unlabeled data rather than labeled data. To do this, we'll build upon previous approaches that essentially condition the network as context on the data. So in particular, our architecture will look like this, where we take unlabeled images from our subdistribution, then pass this into a neural network and aggregate this information into a contextual embedding of the subdistribution. We'll then combine this with the query image, which will be used to predict y hat, an estimated label for that query image. And then we'll compare that prediction with the correct label to perform the classification loss for the query image. Then we'll train this network end-to-end for a variety of different subdistributions that we sample from the data. So how does this do? So we compared adaptive risk minimization to empirical risk minimization, distributional robustness, and specifically a previous method that actually combined DRO methods with neural networks, as well as a solution that tries to upweight the groups to the uniform distribution rather than training on the empirical distribution of groups. So we experimented with a few different data sets. The first data set we looked at was very simple. We just took MNIST and different groups corresponding to different rotations of the digits, and we trained on a very skewed training distribution such that some rotations are much less represented than others. And what we found is that ERM and in other methods, essentially their performance drops in the parts of the distribution that are underrepresented, as we would expect. But our method, which is able to adapt to different distributions, to different rotations essentially, is better able to adapt to this sort of situation and achieves better worst case accuracy and average case accuracy. We also looked at two more experiments, one that is based on the SLEB-A data set and one data set that's called federated MNIST that essentially has different people writing different characters, not just digits, but also the English alphabet, so all the letters in the English alphabet. And what we find in both of these cases is ARM is able to achieve better worst case accuracy and average case accuracy in both cases, and is also able to achieve good empirical accuracy as well, and get close to empirical accuracy of ERM in the case of SLEB-A. And one of the things that's pretty cool about this federated MNIST setting is that you're actually adapting to new users at test time, and this is a bit different than what group robustness typically looks like. And one example of what this actually looks like in practice is here's an example image at test time that the algorithm is given. ERM would just be asked to classify this as is, and it's a bit ambiguous if it's a 2 or a lowercase a. And however, if we give kind of the context of other digits written by that person, it's a little bit clearer that this is actually a lowercase a rather than a 2. And we find that ERM incorrectly classifies this as a 2, especially because 2s are actually overrepresented in the data set compared to lowercase a's. Adaptive risk minimization, when only given the 2 digits in the dashed black square, also outputs as a 2, whereas when given 50 unlabeled images, ARM is able to effectively and correctly classify this as a lowercase a. Okay, so to wrap up, I talked about how we might discover equivariant and invariant structure via meta-learning, and then use this when trying to transfer to new tasks, and show how this can essentially be used to discover certain kinds of structures like convolutions. And I also talked about how we can adapt a distribution shift using the structure recovered by meta-learning, specifically looking at shifts in groups. I'd like to thank my students. If you're interested in learning more about meta-learning, generalization, and so forth, I'd encourage you to check out my course. All the lecture videos are available online, and I'd be happy to take a few questions. Thank you.
Thank you for the great talk. So we have time for a few questions. If you have a question, maybe you can send me a chat and then I'll give you a turn to ask a question. In the meantime, like I have a question. So you talked about this distributional risk DRO, that is distributional robust optimization, and you mentioned about adversarial distributions in it. Like, so how are you learning these adversarial distributions? Is it on unlabeled data or labeled data, or how do you adapt it?
Yeah, so I guess to be clear first, robust optimization is it's actually not quite, so it's essentially outputting an adversarial distribution, not considering all possible adversarial images, simply just adversarial distributions over Q of Z, as shown here.
Yep.
We're constructing different distributions Q of Z and then trying to adapt to those distributions rather than necessarily constructing an adversarial distribution. And we actually consider a Q of Z that is, in our experiments, it kind of differs based on the particular application. But in the MNIST example, the distribution over Z's that we're producing is essentially a uniform distribution over rotations. In Celeb, we basically consider all possible proportions of gender and hair color, introducing kind of different kinds of distribution so that you don't have spurious correlations, which existed actually in the original data set. And then in the federated MNIST case, the different distributions correspond to different people's handwriting.
Oh, I see. Okay, thanks. Any other questions? Oh, Steve has one. Steve, go ahead.
Hi, Chelsea. Thanks. Great talk. Thank you. So I just had a question about the equivariant stuff. So learning symmetries and so on. So I guess symmetries are incredibly important in computer vision, but often symmetries depend on viewpoint, particularly for images are generated from 3D objects, and we can lose those symmetries when we project into 2D. I'm wondering if you have any thoughts on how we can learn 3D symmetries from 2D projections of scenes.
Yeah, that's a great question. So I think that so you could certainly apply this method to 3D data and learn things like rotational equivariance in that, like the point clouds and stuff, and learn that sort of equivariance. Learning those equivariances from 2D data, I think, is more challenging. It's something that we've actually started to try very recently, so we haven't quite gotten any conclusive results there. I think that it's challenging to try to quantify mathematically what that equivariance corresponds to, and it's not clear if this particular linear form can actually capture that kind of equivariance, because it may not actually correspond to a particular group. I guess technically, if you applied this as like literally, if you apply actually like a fully connected layer to the image, which would be kind of impractically compute intensive, then I suspect, I might speculate that you could actually learn the equivariance structure. But that's definitely something for future work. And one of the challenges with that one of the benefits of convolutions is that we not only get this equivariant structure, but we also get this pretty nice speed up when actually implementing GPU kernels with this particular structure. So one interesting direction, I think, for future work would be to see if you can learn this structure from images and then kind of simultaneously also optimize a hardware implementation of that structure that's learned inside the neural network. But that's somewhat speculative, I think.
Cool. Yeah. Okay. Thanks.
Any other question? Okay. If you don't have any more questions, let's thank the speaker. Yeah. Thanks. So that's pretty much it for this session. Thank you all for attending, and we'll have a break for now, and we'll join back for the oral papers at 2:15 Pacific. No, it's not 2:15. It's in 15 minutes Pacific time. So so that's at 11 o'clock in the Pacific time. Yeah, great. Thank you so much.